Good morning, dear. Welcome back. So this is our fourth lecture on mathematical foundation of robotics and industrial automation. As I told, the fundamental part we are together. So we are trying to understand what robot is, how robot can be modeled in a computer, and how it actually works. Okay. So in that context, we were telling you that this is a two-link manipulator. Two-link manipulator actually is what we can go and we can actually visualize. Okay. That's why we are taking the help of this simple. We are taking the help of this simple manipulator. Okay. This is not a robot. Okay. So what you have seen, we were parameterized this robot by two elegant equations. Okay, and this theta 1, theta 2 all are the function of time. Then we formulated two problem. Okay, and we are in generalized way, we are considering two space. One is known as Cartesian space where robot is working, another is joint space where robot is actually moving. Okay, robot can move only in the joint space by manipulating the joint. Okay, and this was fine. Forward kinematics. Linear problem because theta 1, theta 2 are known. This is L1, L2 or design parameter, they are known. And when this problem is inverse kinematics. Inverse kinematics is more common because I will command robot to move somewhere and robot need to figure out what are the feasible joints which it should move to reach somewhere. And as for us, you know that it is a quite reactive process which we learn from the childhood. I should say it's a learning process. Why I am telling learning process? Because if you see kids, when they are just crawling over and then you place some item within their reach, so they will just put hands like this in the vicinity of this to reach there. Okay, so they are not able to reach at single effort. Okay, so that means we are trying to learn. Here we are trying to plan robot so that whenever this parameter will be given, this parameter can be evaluated by formulating inverse kinematics solution. We will solve inverse kinematics, which is not very straightforward, and in that context we will talk about 8 and 2 function. But having said that, once you know the inverse kinematics, is the problem over. That means you now know that how much movement of theta 1 and theta 2 robot should make to reach to the destination. Okay, so destination is here. Okay, it is not over. Why? Because robot need to know where its current position is. Say robot is first time switched on. Whenever you switch on a robot, backside robot for example, then it makes some sound and actually it has a execution level controller. It tries to figure, it has defined a home position for the robot where each joint takes some value. Okay, so that is called inertial position or home position of the robot. Now, robot has home position, and now you are solving inverse kinematics. That means you are telling, that means these joint values, they have already some joint values. Say my hand is now in this position, and then I am instructing my hand to reach here. So with respect to this, okay, it will move, right? On the contrary, if my hand was here, with respect to this position, it will try to reach to the ordered position. So how that can happen? Okay, so out of multiple solution, that's why it first need to read its home position or current position, and then it should solve inverse kinematics problem, which will yield multiple solutions, and out of those multiple solutions, from the present joint configuration, what is the minimum movement the robot should make, that decision robot also has to take. Okay, minimum and much without much hassle. What do you mean by that? Say my hand is here, right? And now destination is no steep. So my hand should move very, you see, smoothly. This we call smooth. Smoothly, not like this with jerk, right? So that smoothness also is an issue which we'll discuss. Who will give that smoothness? That is called Jacobian. We will discuss about that manipulator Jacobian. Okay, and we will discuss about that trajectory planning. Actually, I am talking about what I am talking right now is called trajectory planning. Robot need to plan a trajectory. So inverse kinematics is the basic raw material. Okay. Now to reach there, also you need to plan a smooth trajectory. Okay. Because it has multiple solutions, it has some freedom within those multiple solutions to figure out the smoothness of the joint motion. So that is called trajectory planning. Okay. So inverse kinematics, inverse kinematic solution, trajectory planning. Now, also, you need to know a little bit about robot dynamics. Why? Because in our model, you see, what we have linked length only. But there is no mass, okay? But you have seen Dexter is quite heavy. It has a link mass, length together with the mass, right? And whenever robot will move, what will happen? It will feel inertia because it has a mass. Now when you are moving with a mass, that model we do not have here. Okay? So that model we will study in the dynamics. And dynamics, actually we will reduce this equation. This is very well known. Okay? So this is called robot dynamic equation. Okay? If it is trajectory planning, this is dynamics. This is more refined model. This is simple model, but incomplete model because it do not consider, the model does not consider the robot's mass of the link. Okay, but this considers. Okay, so this is dynamics, robot dynamics. Each and every term is very interesting here. This is coupled form. In a coupled form means in a matrix form it is written. Say if I have two joints here, so one motor will be here, another motor will be here. Motor will produce torque, so I will be having tau 1, tau 2. Okay, so tau will be equals to 2. If I have Dexter type of robot which has 7 joints, then tau dimension will be clear. So in vector form I can write this this 7 cross 1. Then you can also see, so this dimension will be 7 cross 7, 7 cross 1. This is also will be 7 cross 1. And this is also will be 7 cross 1. So this is called mass matrix or inertia matrix. Okay. So this is actually also tensor. Okay. There are so many names. This is a matrix. It represents how the mass is distributed in the robot. Okay. And this is very important about dynamics equation to be solved. To know, here also the concept of forward dynamics and inverse dynamics exist. Now let us try to understand what is. So this is by Newton's law, okay, that cause and effect are relative. So if this is the cause, that means if you switch on the motor, it will produce some torque. If you switch on the motor, it is producing some torque, and the manifestation of that torque will be exhibiting some motion. Once the torque is there, it will start moving, and that movement will be associated with some acceleration, with some coupling force, with some gravitational torque. Okay, because movement has to be against gravity, so it will resist. That is gravitational torque. It will experience. Okay, torque, because this mass can be assumed to be, for simplicity, accommodated here. So these are under gravity, so they will produce some torque at this joint level, right? So that is what gravitational torque. So this is gravitational torque. What is this? This is centrifugal and Coriolis torque. Okay. Now, when my hand is moving, this end moving with this with respect to this joint, okay, and this joint also moving. Now this motion has a coupling, so there is a coupling effect on this joint. Okay, I will reduce this completely. It will be from the fundamental. Okay, so you will see that it will have also centrifugal force, because now my hand is undergoing together with some rectilinear motion, curvilinear motion also, right? Because my joints, this is a revolute joint type of robot. Okay, it's not prismatic joint. Okay, that means robot will only can rotate. The joint can only rotate. Okay, and the manifestation of that rotation may be robot is moving in the transitory direction, in the rotary direction. Okay, so this is coupling. Okay, from joint. So if this joint, so coupling force will be here because of this link. Okay, so this will all be captured in the in this term. And there is another term when there are two relative motions. Okay, Coriolis force comes into existence. Okay, they may be small, but they are significant when you have a robot having substantial mass and moving with a substantial velocity, right? So these are significant at the time. Coriolis is actually mutual relative motions effect, right? I can give an example. You can see Coriolis effect in many applications. Say you are playing a carom, right? You know, there is there are pockets, okay, or billiard. Okay, there are pockets, and you are trying to hit the ball for a particular destination, right? And when you are aiming that, when that billiard board is in rest, no Coriolis force and nothing, then your vector direction will be 1, which will enable the ball to go to the pocket. Now, if somebody put a motor and the billiard board is rotating and you are also rotating. Now you are trying to aim the dice or the ball to the same destination. You will see the earlier vector direction. If you stick to that earlier vector, then ball will move a little bit, okay? And because you have not, because the ball is now, because of the movement of the billiard board and this movement of the striker, there are relative motion now. Okay, so you need to have a different kind of vector direction. Okay, which is known as Coriolis Force after that scientist's name. Okay, so this is inertial torque, Coriolis and centrifugal torque, gravitational torque. These are the three major torque which is related with the joint torque. So if the joint torque is given, as a result of that robot is moving, that problem is called forward dynamics. Forward dynamics. Right? So when, if I call this, this is equation set 1 and this is equation set 2. So in 2, if left hand side is given, that is tau theta is given, and as a result motion is created, is called forward dynamics. Exhibited. So left hand side is given and as a result right hand side motion is exhibited, then it is forward dynamics. Okay? Forward dynamics. Then inverse dynamics. What is inverse dynamics? We are defining, say, I have two joints here, right? So I am defining for joint number 1, okay, what will be the kind of trajectory, what kind of motion will be there. I am defining this. Also some kind of, then I have joint number 2. Joint number 2. So all this kind of thing, if I hypothetically I am telling that you can simulate and you will get exact. But I am trying to tell you that when these are my desired motion parameters, which we are defining, that robot should move, end effector should move with such and such velocity, with such and such acceleration, with such and such deceleration, because robot if pick something from here, then accelerate, so it starts from rest, then it accelerates, and then it decelerates and come to rest to place that object. So all this, starting from rest, accelerating, sometimes it may also move if it is a long way to go, sometimes it can move with constant speed, and then it has to decelerate so that it will reach to the destination and keep the object. So all these things has to be planned. Okay, and if we plan those parameters, that means right hand side, if on the contrary right hand side is given and planar task is to create planar task is to create the required left hand side then the problem is known as inverse dynamics problem. So, unlike this, so please be careful. Okay, if left hand side was given, you need to find right hand side. That means this was given, it was inverse kinematics. But if this is given, then it is forward dynamics. If this is given, this is your finding, right? If this side is given, unlike here, when this side theta 1, theta 2 are giving, you are solving forward kinematics. Is it clear? So, this is just, don't make a confusion that when this is given and you need to calculate what are the torques which are required to create this motion is called inverse dynamics problem, and we need to solve inverse dynamics, forward dynamics. Forward dynamics is mostly solved for simulating a robot. Okay, that means I would like to show that if this is the joint torque characteristic, then how the end effector motion characteristic would be by solving the forward dynamics. But otherwise, for all control purpose, you need to solve inverse dynamics, because the moment your planar is telling that okay, for creating this motion, say robot is writing its own name, robot, R-O-B-O-T. These are very complicated trajectory, and to follow this trajectory I will have to define the motion, okay, and then I will have to calculate the torque, and then I will have to control the motion as per those calculated torque, and then only the robot can follow the desired trajectory. Okay, so inverse dynamics is very important, practical, right? Inverse kinematics is very important, and everything starts from inverse kinematics, trajectory planning, and then to make the model more perfect, then we talk about inverse dynamics. Okay, so that enables us to create a relation between motion and cause of the motion. Okay, and then we will talk about, so this is all about how robots are planned to make a movement. Okay, and then we will talk about how robot can be controlled using sensors, those control. This is just like our anatomy. Okay, human also, when I am making motion, my bones, limbs are actually moving, actuator is muscle, okay, and brain is the controller, brain together with spinal cord. There are two controllers, brain which plans, and then spinal cord which is situated here, okay, below medulla oblongata, and then what they do, they reactively make the motor actions, okay. So in a coordination, they are done for us, and we want similar coordination, similar hierarchical structure of control to be also implemented in the robot, and all the robots are having similar kind of analogical hierarchical control structure. That and those other interesting things we'll discuss in the next class. Till then, stay safe. Bye bye.